Hi everyone, welcome back to the second lesson on the idea of confidence intervals. And in this video, we're going to continue on taking a look at the properties of a confidence interval. And to start with, we're going to take a look at what happens when you change the level of confidence. So we're going to go back to our confidence interval applet that you saw in the first video, and we are going to go from a 95% level of confidence to a 99% level of confidence, and we're going to see what happens to, one, the overall length of the confidence interval, and two, what percent of confidence intervals ended up containing the population parameter that we're estimating. So here's the applet, and in this case we are using the applet to simulate a 95% confidence interval with samples of size 20. So we're going to take or simulate 25 random samples here, and you will see in our 25 random samples, it turns out that all but one of these sample means was close enough to the population mean, so that when we went out 2 standard deviations in each direction, those confidence intervals did contain the population mean. Reminder here, what changes is your point estimate or your sample statistic. And so the confidence interval either contains the population parameter or it doesn't. There is no probability associated with that. What we say is we have a certain level of confidence that the confidence interval contains the population parameter. We do not say the probability that the confidence interval contains the population parameter, because there's no probability associated with whether or not the confidence interval contains the population parameter. So anyway, what we're going to do here is we're going to increase the level of confidence, and we're going to go all the way up to 99, but pay attention to the graphic there as we increase from 95 on up. And I'm going to have to do this with my mouse instead of my stylus. So we're going to go up to 96 and 97. And you'll see when we hit 97, our confidence intervals, even though our statistics didn't change, our point estimates didn't change, our confidence intervals got long enough so that all the confidence intervals contained the population parameter. And when we go on up to 99, you see the confidence intervals get even longer. Now, the reason that all of them contain the population parameter here is because we have not taken all sample statistics from this sampling distribution. So if we had, then it would turn out that precisely 99% of those confidence intervals would contain the population parameter. So we can see that two things happen when the level of confidence increases. The confidence intervals get longer, and more of the confidence intervals contain the population parameter. So what happens to the length of the confidence intervals as the level of confidence increases? It gets longer. What happens to the percent hit as the level of confidence increases? It gets higher or greater. So we're going to go back to the SAT problem from the previous video, and we're going to take a look at the margin of error in the confidence interval a little bit more. And just to remind you, the margin of error was the part that we added or subtracted to our point estimate, our sample statistic. So our sample mean was 461, and the population standard deviation was 100. Okay, so this is sigma is equal to 100, and the margin of error turned out to be 9. We're going to show how we got that margin of error of 9. So x bar plus or minus what is called the critical value, how many standard deviations we're going in each direction based on the level of confidence, times the standard deviation of the sampling distribution, which is sigma of the population over the square root of the sample size. So that translates to 461 plus or minus We used 2 because we're going 2 standard deviations in each direction because of the 95% level of confidence. We used 2 as our critical value. And the population standard deviation, 100 over the square root of the sample size. And our sample size in this case was 500. So if you were to simplify this, this part right here would turn out to be 9. So what we call that is we call that the margin of error, and it consists of 2 parts. It consists of the critical value and the standard deviation of the statistic. Okay? So what happens if we want let's say a 90% confidence interval? Well, as you know from the empirical rule, if you want to be 68% confident, you would go out 1 standard deviation, so the critical value would be 1. And if you wanted to be 95% confident, you would go out 2 standard deviations, so the critical value would be 2. And if you wanted to be 99.7% confident, the critical value would be 3. So a 90% confidence interval would require a critical value between 1 and 2. So what will change in this formula if we want a 90% confidence interval? The critical value, CV, will decrease from 2. An 80% confidence interval, the critical value will again decrease from 2. Now I don't know exactly what those numbers are, but we are going to talk more about how to find those later on. All right, so we're going to take a look at these statements here based on the margin of error and fill in the blanks. As the confidence level increases, the critical value increases. We've got to go out more standard deviations to be more confident. The margin of error also increases. If we increase the standard deviation or we increase the critical value, the margin of error increases. And the confidence interval gets longer, or if you prefer, wider. So clearly we would like to decrease the margin of error. We'd want to reduce the length of the confidence interval. And what are some ways we can do that? One, we can reduce the critical value. But if we're going to reduce the critical value, then we have to reduce the level of confidence. That's not so great. What else could we do? We could decrease the standard deviation of the statistic. Well, that's based on the population and the sample size. So if we wanted to maintain the same critical value, the only way that we could reduce the margin of error is to increase the sample size. Here's a cartoon related to a confidence interval. Let's take a look at this and see what this says. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. And there's Heathcliff saying this guy's never wrong. So what is wrong with this confidence interval? Well, the level of confidence is extremely high, right? If the guy's never wrong, but the margin of error is absurd. It's kind of like me saying, I'm 100% confident that the average on the next quiz will be between 0 and 100%. There's a trade-off there. Large margin of error, high level of confidence. So we have to reach a sort of happy medium. So we're going to wrap up with the conditions for constructing a confidence interval, which have come up already in chapter 7, basically, but we're going to repeat them here. So the data needs to come from a well-designed random sample or a randomized experiment. It needs to be random. The observations need to be independent of each other. If we're sampling without replacement, the sample size should be less than 10% of the population. And if we're going to do normal calculations, the sampling distribution needs to be approximately normal. So why is the first condition important? we need a sample that accurately represents the population. Why is the second condition important? Without it, the formula for standard deviation of the sampling distribution, sigma p hat or sigma x bar, do not apply. And this goes back to the idea of random variables and combining random variables and adding variances when the random variables are independent of each other. And the third condition, why is it important for the sampling distribution to be approximate? Why is the third condition important? We can't do calculations unless, again, why is the third condition important? We need a normal sampling distribution if we're going to do normal calculations. To do normal calculations, converting to a z-score and using the standard normal table doesn't make sense unless you're working with a distribution that's approximately normal. Okay, so if any of the above conditions can't be verified, you should be reluctant to construct a confidence interval and interpret it in the way that it should be interpreted. Now, here's the reality of the situation. We are going to give you problems where you don't meet those conditions on purpose to check to make sure that you're verifying those conditions. In those cases, you should verify whether or not the conditions are made or are met or not, but you should still construct the confidence intervals just for the practice.